In this video, we're just going to go over some practice problems on the material covered this week. So we're going to start with section 4.1, and for all of these problems here, what we want to do is simplify each expression and evaluate if possible, and then write each result using positive exponents. So we'll start with question 11 here. We have 13 to the 4th power times 13 to the 8th power. Now, what we're going to use here is our product rule for exponents, and it says that if we have the same base, so in this case that would be 13, then we can simplify this. It'll be the same base to the 4 plus 8 power. So this would be 13 to the 12th power, and then we can just put that into our calculator and we're going to get a really big number. Okay, let's go on to question 17. So in this case, we might want to do the product rule again. We have this base and we have our exponents here. But in this case, we actually can't simplify this further. And the reason being is that we don't have the same base. We have an R and an S. These are the two different bases for each of these guys. In the last example, our base was 13, so we were able to apply our product rule. So in this case, we can't simplify R and S. So R and S are not the same base. So we would just leave it at that. All right, let's go on to question 22. So here we're multiplying these two expressions. So what we can do is kind of group these guys. Notice we have our constants 8 and 3 here. Then we have these exponential expressions with s to the 4th power and s cubed. So these guys would have the same base in this case. So let's stick with our color coding. And similarly, we have this t and then this t to the 5th power. So these guys also have the same base. So this tells me if we have the same base, we can use our product rule. So the first thing we can do is we'll just multiply this 8 and 3 here. This will give us 24. Then we can multiply our s to the 4 and s to the 3. So I'll write this here. And similarly for our t and our t to the 5th power. So using our product rule, we're still going to have this 24 out front, but this will become s to the 4 plus 3, so s to the 7th. And then t to the, in this case, this t has a power of 1. So this would be t to the power 1 plus 5. So t to the 6th power. And so this would be our final answer for this one. Now for this next question here, 32, we're going to use our zero exponent rule. And so that says anything to the power 0 is just going to be 1. So for this example here, we still have this negative out front, and we're saying we're taking negative 2 to the power 0. So everything inside of this parenthesis to the power 0, well, we know anything to the power 0 is just 1. So this whole thing here becomes just 1. And so this answer here will give us a negative 1. All right, now going on to 39, we're still going to use our rule for anything to the 0 power. So this means we have minus 4 to the 0 power here. So this negative is going to stay out front. It's not in our parentheses, so it's not going to come with us here. So this will be minus out front, and then 4 to the 0 power, which is going to be 1. And then we have this minus out front of our m to the 0 power, and then again, anything to the 0 power is just going to be 1. So this will give us a minus 2. All right, for the next question here, we're dealing with negative exponents now. So there's a couple of different ways we could approach this problem. The first thing that we could do is rewrite this with positive exponents. So doing that, we'll get this here. Now, what's happening in the denominator of this fraction is we're taking minus 3x and we're cubing it. So this is expanded would be minus 3x times minus 3x times minus 3x on the bottom here. And we can use similar properties that we saw in this question 22 here. We have minus 3 times minus 3 times minus 3, so that would give us a negative 27, and then we have an x times an x times an x here, so that would give us x cubed. So what we'll have here in the denominator is minus 27 times x cubed. And remember, when we're multiplying these x's here, these are all to the power 1. So this is the same thing as x to the power 1 plus 1 plus 1. So that's how we get x cubed here. In this next example here, we're still dealing with our negative exponents. So again, the first thing that we'll do is just rewrite this with positive exponents. So our term 6 to the power negative 1 becomes 1 over 6. And then we're subtracting out our second term, 4 to the power negative 1, so 1 over 4. Now from here, we can just evaluate this. What we'll do is get a common denominator. So I'll multiply the top and bottom of this fraction by 4. That'll give me 4 over 24. And then I'll multiply the top and bottom of this fraction by 6. So that'll give me 6 over 24. And we're just doing this so that we can actually subtract these guys. We can't subtract this in this form. We can only do it with a common denominator. So on the top here, once we have a common denominator, we will just subtract the numerators. So we have 4 minus 6. So this will give me a negative 2, and we still have a denominator of 24. So simplifying this a little bit further, we'll divide by 2 on the top and bottom of this fraction, and we'll get minus 1 over 12. Now in this next example, 72 here, we again have our negative exponents. And so if we want to make the top here, we want to write this as a positive exponent, it would go in the denominator. And if we want to write this guy as a positive exponent, it would go into the numerator. So in this case, rewriting this whole thing with positive exponents, we're going to get this here. So we're going to get the reciprocal of that guy. Now here we can use our quotient rule for exponents. When we have an exponential expression of this form, we're just going to subtract the exponent. So this will be 5 to the power 9 minus 7. So this will be 5 squared, which is the same as 25. All right. Now for question 79, we could do something similar. We could subtract. We could have minus 3 minus 7, or we could rewrite this with a positive exponent first. You're going to end up with the same answer. I'm going to choose to rewrite this with positive exponents. So we'll get this here. Now, in the denominator, what I can use is the product rule. So I can just add our 7 and 3, since we have 6 is our base. We have the same base. So this will be 6 to the power 10, and then we can put that into our calculator. We'll get a big number, but I'm going to leave it there. In this next example here, we again have a fraction with an exponential expression in the top and bottom. So we might want to subtract these exponents, just like we did in this example here. But in this example, our bases were the same. We had a 5 and a 5. And in this example, our y and t bases are not going to be the same. So we've run into another example where we can't simplify this. And that's because y and t are not the same base. So we'll just leave it at that. All right, so this brings us to this next question here. Now in this case, what we're going to use is our power rule for exponents. And that says if we have an exponential expression to another exponent power here, this power is going to be distributed to everything inside of our parentheses here. So this 3 is going to be distributed to this 6 and to this x squared here. So what we're going to be left with is we have 6 cubed times x squared cubed. Now we know that 6 cubed is going to be 216. And in this case, what we're going to do is we're not going to add these guys using our product rule. We've seen before, if we have this case where we have 2 exponential expressions with the same base, we can add their exponents. In this case, we don't have 2 exponential expressions with the same base. We have an exponential expression raised to another power. So here, what happens is we multiply our exponents. So this would be x to the power 2 times 3, so x to the 6th power. And this is our final answer. And what we can do to kind of get a better understanding of this power rule is we could actually take, if we have 6x squared to the 3rd power, this is the same as this here. And so what we can do is, we've seen in the last several examples, we're going to multiply our 6's. So we have 6 cubed in this case, which is 216. And then we have x squared times x squared times x squared. Now in this case, we could use our power rule since we have these three exponential expressions with the same bases. So this would be 216 times x to the 2 plus 2 plus 2 power, which is x to the power 6. So using this power rule here is just an easier way to evaluate these types of expressions without having to do it this way. Okay, so that brings us to question 97 here. This one is very similar. We have this exponential expression raised to this power 4 here, but we have a fraction inside of our parentheses. So this 4 is going to apply to everything inside of our parentheses. So this fourth power is going to apply to this guy and this guy in our numerator. So what we're left with is we have this minus s cubed raised to the fourth power, and in the bottom, t to the fifth power raised to the fourth power. So we're again going to use our product rule. We know that if we have something of this form here, these exponents are going to be multiplied to each other in the top and bottom here. However, this minus sign makes it a little tricky. We have to be careful. The coefficient in front of this s cubed term here is going to be minus 1. So what's happening is we can think of this 4 on the top being distributed to this guy and this guy. So what we have is a minus 1 to the fourth power times s cubed to the fourth power over our t term on the bottom here. So in this case, this becomes a positive. So we're just going to have a positive 1 in front of this term here. So this will become s to the power of 3 times 4, so s to the 12th power, over t to the 5 times 4, so t to the 20. All right, so in this next example, we again have this expression raised to now the negative fourth power. So we know that this exponent is going to be applied to the numerator and denominator of this fraction, just like the last example we looked at. So what we have here is 2t to the negative fourth power over 3 to the negative fourth power. Now, the first thing when we have these negative exponents that we want to do is rewrite them with positive exponents. Well, we saw in example 72 here that if we have negative exponents in the top and bottom of our fraction, then this is the same as the reciprocal of it with positive exponents. So we're going to rewrite this as 3 to the fourth power over 2t to the fourth power. All right, so 3 to the fourth power is going to give us 81 on the top. And then we know that this 4 on the bottom is going to be applied to this 2 and to this t here. So we're going to have 2 to the fourth power times t to the fourth power in the bottom. So finally, we're going to get 81 over 16 times t to the fourth power as our final answer. All right, let's look at question 126 here. So we have this guy. We're getting a little more complicated with our exponential expressions, but we're just going to break down the rules that we've seen so far. So for this first term here, we know this 2 is going to be applied to this 3 and to this p to the negative 4 power. Then for the second term here, we again have an exponential expression raised to a power. So that negative 1 is going to apply to this guy here. All right, so rewriting this, we're going to have 3 squared times p to the negative 4 squared times p to the negative 3, so that's just going to be p to the negative 3 here, because we have 3 times this negative 1. Right, and then we don't want to get confused. This negative 1 isn't being applied to this. Only this guy is raised to this power here. If this guy was raised to the negative 1, it would be inside of our parentheses. All right, so now we're going to have 9 times p to the negative 8 power. Remember, our power rule tells us we're going to multiply these two, and then this will be times p to the negative 3 power. So our product rule says we are going to add these. So this will be negative 8 plus a negative 3. So this will be 9p to the negative 11. And then finally, writing this with positive exponents, we're going to get this here. Now notice we could have written this with positive exponents first, and so we would have 9 over p to the 8 times p to the 3, so that would give us 9 over p to the 11 in the denominator. So we'll end up with the same answer either way. All right, so this brings us to our last example for section 4.1. We have this fraction, this big exponential expression raised to the minus 2 power. So the first thing we're going to do is notice that this minus 2 is going to be applied to everything in the numerator and the denominator. So we're going to have this here in our numerator, and then this here in our denominator. So from here, using our power rule, we know this minus 2 is going to be applied to every base that we see here in our numerator and in our denominator. So this will give me 8 to the minus 2 times x to the minus 6 raised to the minus 2 power, and then y cubed raised to the minus 2 power, all in the numerator. In the denominator, we'll have these guys raised to the minus 2 power as well. So let's simplify this a little bit. We know we're going to use our product rule, so we're going to have x to the negative 6 times negative 2. So that'll be x to the positive 12th, and then similarly, we're going to have y to the negative 6 here. In the denominator, again, we're multiplying these guys, so this will give us x to the negative 8, and then y to the positive 8. Now the next step would be to rewrite this with positive exponents. So everything on the top here that's negative, so our 8 squared and our y to the negative 6, is going to come to the bottom of our fraction, and then this guy is going to go to the top. So we're going to have x to the 12th times x to the 8th power on the top, and then 8 squared times y to the 8th times y to the positive 6 on the bottom. All right, and then finally simplifying this, we know we can use our product rule, so we can add our 12 and 8. So in the numerator, we're going to get x to the power 20. And in our denominator, we know 8 squared is 64. And then we can add the exponents of these guys since they have the same base. So this will give us y to the 14th power. All right, so section 4.2 talks about scientific notation, and if you haven't seen it before, it's a method that we use for writing very large or very small numbers in a compact form. So here we would write a number n times 10 to some power little n here, where this number n is a number in between 1 and 10. So we can rewrite very large or very small numbers in this form by doing the following. So let's look at these examples here. We have this large number, and as we know, every number is going to have a decimal here, right? This number can be rewritten as 0.0. So we're going to move this decimal however many places to the left so that the number we're left with is going to be a number in between 1 and 10. So for this first one, we're going to move this decimal, let's see, 1, 2, 3, 4, 5, 6 units to the left here. So we're going to be left with 1.06 as our number, and that's going to be good for n here because it's in between 1 and 10. So we know we've moved the decimal the correct amount of units to the left. And it'll be times 10 to the 6th power because we moved this decimal 6 units. All right, so that's how we would write this number here in scientific notation. Now, for question 13 here, we have a really, really small number. So for question 10, we had a big number, and here we have a small number. So we again want to write this in scientific notation of this form here. So we're going to have to move this decimal now in this direction to the right here. So, let's do it in blue again. We're going to move this decimal 1, 2, 3, 4, 5, 6 units to the right. Now, the reason why I'm not putting the decimal in between the 9 and 2 here is because then I'd be left with 69.2. And 69.2 is a number not in this interval, but 6.92 is a number in between 1 and 10. So our capital N here is going to be 6.92 times 10. Now in this case, our exponent is going to be negative because we're moving in the opposite direction, and we moved 6 units. So a way to remember if we're dealing with positive or negative exponents with scientific notation is that when we're dealing with a positive exponent, we're dealing with a very large number, and when we're dealing with a negative exponent, it's going to be a very small number. All right, so this brings us to our next two examples here. Now we're given a number in scientific notation and we want to write it in standard notation. So we're going to write it like this here. So in this case, we have 8.91 times 10 to the second power. So we know that we're going to move our decimal here 2 units to the right. Remember, when we're dealing with positive exponents, we're going to make this number bigger. So this is just going to be 891. Now for question 22 here, we have 5.04 times 10 to the negative 4. So I'm going to move this decimal in the opposite direction, 4 units. So 1, 2, 3, 4. And so we're going to place some zeros here. So this number would be this here. And we know that this is the case because this is going to be a really small number since we have a negative exponent. Now for the next two examples, we want to evaluate these guys. So we have this fraction here where our numerator and denominator are numbers in scientific notation. So there's a couple different ways that we could do this. We could just rewrite this as the number that it is by moving this decimal 3 units to the left and then moving this one 2 units to the right and then dividing. Or what we could do is we could use our rules for exponents that we saw in the last section. So I'm going to do that for this example, and it's helpful to be able to apply these rules because we could be dealing with very, very large numbers, and we wouldn't want to first write them in standard notation and then evaluate if these were very large exponents. So we're dealing with a division here, so we know we're going to be able to divide these guys out. And then we have 10 to the negative 3 and 10 to the second power. These guys have the same base, so these exponent rules that we saw in the last section will apply. So what I'm going to do is just rewrite this like this here, so we can clearly see what we're separating. So in this case, 5 over 25, this is going to be reduced to 1 over 5. And then for this term here, we know that we can rewrite this as, rewrite this a couple different ways. We can rewrite this as 10 to the negative 3 minus 2. So this would give us 10 to the negative 5 power. Now, we want to rewrite this in standard notation. Okay, so the first thing that I'll do is just note that 1 over 5 is the same thing as 0.2. So this is 0.2 times 10 to the negative 5. And then we can easily write this in standard notation. We know that we're going to move this decimal 5 units to the left. And we're going to put our zeros here. So in standard notation, this will be this here. And so this would be our final answer. Now for this next example here, we have this complicated expression that we want to evaluate. So the first thing that I'm actually going to do is try to rewrite these numbers in scientific notation so that we can use the same properties that we saw in this last example. So the first thing we'll deal with is this 840,000. So rewriting this in our scientific notation, we're going to move this decimal 1, 2, 3, 4, 5 units to the left. So we're going to get this here. And then for our 0.03, we're going to move this decimal 1, 2 units to the right. So times 3 times 10 to the negative 2. Now on the bottom, doing the same thing, we're going to move our decimals 1, 2, 3, 4 units. So this will be 2.1 times 10 to the negative 4. And then our 600 is going to be 6 times 10 squared. All right, so now we have these numbers in scientific notation and we can use the properties that we've seen before. We'll kind of combine like terms in a sense here. We're going to separate our constants and then our exponential expressions here. So we have these numbers here and then these exponential expressions that we're going to separate. All right, so we have 8.4 times 3 over 2.1 times 6 times our exponential expressions. So we have 10 to the 5th power times 10 squared, or 10 to the negative 2 power on the top. and then 10 to the negative 4 times 10 squared on the bottom. Now what we can do for our exponential expressions here is we can use our product rule, so we could add these guys. But notice we also can use our quotient rule. This 10 to the minus 2 and 10 squared is automatically going to cancel out. So that's going to make this simplification a little bit easier. So for this guy here, plugging this into our calculator, we're going to get 25.2 over 12.6. And then for this here, we're going to do 10 to the 5th power minus 10 to the negative 4. So 10 to the 5 minus negative 4. This gives us 10 to the positive 9th power. Okay, so just using our quotient rule here tells us to subtract these exponents. And then finally, plugging in this fraction into our calculator, this is actually just going to be 2. So this will be 2 times 10 to the 9th power. And then finally, we want to write this in our standard notation. Doing so, we're going to get this here, just moving our decimal 9 units to the right. Oh, put a box around this. So this would be our final answer for this one. Alright, so this brings us to section 4.3, where we're working with polynomial functions. And so polynomials are, like I said, mathematical functions, but these are expressions where we're dealing with multiplication, subtraction, addition, and multiplication of different terms. And these terms will have variables raised to whole number powers. So some examples of polynomials are in these 5 questions here. Now in questions 19 through 20, what we want to do is write the polynomial in descending powers of the variable, then give the leading term and leading coefficient. So first for question 19, if we want to write this in descending powers of the variable, we're going to start with the highest, or the term with the highest variable power, and go down from there. So this will be 2x cubed minus 3x squared plus x plus 4. The power of our variable here is 3 and then 2 and then 1. So this is a polynomial in descending powers of our variable x. Now our leading term is going to be the term with the highest exponent power. So our leading term in this case would be this 2x cubed. So I'm going to abbreviate that as LT for leading term. And then our leading coefficient is just the coefficient in front of this term. So in this case, LC for leading coefficient, this would just be 2. And just to keep up with our color coding here, our leading terms in green and leading coefficient is in blue. So this brings us to question 20 here. We want to do the same thing. So writing this polynomial in descending powers of our variable q in this case, we're going to start with this 3q to the 4th power plus q squared minus 2q plus 1. So as you can see, the variables in descending powers here, in descending order. And then our leading term is then going to be this 3q to the 4th power, and our leading coefficient would be the coefficient of that term, so 3. So this is our leading coefficient and our leading term here. So for these next 3 examples here, what we want to do is identify the polynomials as a monomial, binomial, trinomial, or none, and then give the degree. So a monomial is just going to be a polynomial that has 1 term. A binomial is going to be a polynomial that has 2 terms, and so on. So for question 29 here, we have 2 terms. So this one is going to be a binomial. Now, the degree of our polynomial is going to be the degree of our leading term. So from this, we saw in the last couple examples, our leading term is going to be the one that has the highest exponential power. So this one is going to be our leading term in this case, and then we want to find out the power, and that'll be the degree of this polynomial. So in this case, the power of our leading term is 8, so the degree of this whole polynomial is going to be 8. Alright, so moving on to 32 here. This one is clearly going to be a monomial. There's just 1 term here. Now, this leading term, we want to figure out the, or I guess I wouldn't call it a leading term since there's only 1 term here. But we want to figure out the degree of this guy, and it's going to be the exponential powers of both of these guys combined, since this is just 1 term. So we have a to the 4, or a cubed, and then b to the first power. So the degree is going to be the combination of those. So the degree in this case is going to be this cube plus this 1 power. So this will be 4. This is a monomial with degree 4. All right, and so we want to do the same thing for question 35 here. We have this more complicated polynomial, and first thing we're going to do is identify if it is one of these three. Now notice we have 1, 2, 3, 4 terms. So this is going to be none of these. It's not a monomial, binomial, or trinomial. So we're just going to say none. And then we want to give the degree. So first we have to find the leading term. So as we can see here, this is already written in descending orders of its variables, p and q, and this is going to be our leading term. Now, we have p to the 4th power, and then q to the 1st power, so the degree is going to be the sum of those two. So in this case, the degree of this is going to be 5. Alright, so this brings us to adding and subtracting these polynomials. So for this question here, what we want to do is add these two polynomials. Now, we can easily add these guys by combining like terms. So let's do some color coordination to point out our like terms. In our first polynomial, we have 6t squared. And then in our second, we have minus 4t squared. These guys are going to be like terms because they have the same variable raised to the same power. Now we also have this minus 4t to the 4th and then 3t to the 4th in our second one. And then we have this minus t, and we don't have any other like terms in the other polynomial, but that's fine. And then we just have this constant 5, and we don't have any constants in the first polynomial. So what we're going to do is just combine them, since all we're doing is just adding these polynomials together. So we're going to take, we have this, and we'll write this in descending order. So we'll start with the terms that have t to the 4th power. So essentially what we're saying is we have this minus t to the 4th power and these other terms here, but we're going to add it to 3t to the 4th power with these other terms. So we're going to add these guys. This is going to give us minus t to the 4th power. Then we're going to do the same thing with these like terms. We have 6t squared minus 4t squared. So this will give us a positive 2t squared. And then we have this minus t. We can't add that to anything, but that's fine. Same thing with this positive 5 here. So this is our final answer, and this is what we get when we add these two polynomials together. So in this next example, what we're doing is subtracting these two polynomials. So we're subtracting this polynomial from this one here. And in this case, we have to be a little bit careful because the action of subtracting is going to change the sign of all of the terms inside of our parentheses here. This negative essentially gets distributed to every single term inside of our parentheses. So what we're going to do is rewrite the subtraction of these two polynomials by distributing this negative among the second one. So this becomes a minus 3q to the 4th power, a minus 5q squared, and then a plus 5. All right, so from here, we can just combine like terms just like we saw in the last example. So let's continue with our color coding here. These guys are all like terms. So now we have q to the 4th power minus 3 of those. So this will give us a minus 2q to the 4th power. Then we have minus 2q squared, and then we're going to subtract off another 5q squared. So this will be a minus 7q squared. And then finally we're going to add these constants together. So this will be plus 15. And so this would be our final answer and what we get when we would subtract these two polynomials. Now for these next two questions here, what we're going to do is we're still going to subtract and add polynomials, but we're going to do so in what's called vertical form. And as you can see, we have two polynomials here, and they are laid out in vertical form. So all of our like terms are in the same column, which is nice. So in this case here, what we're doing is we're just going to subtract everything in these respective columns. So in this first column, we have our z squared terms. So we have minus 4z squared minus 3z squared. So we'll just write it right under this line. This will give us a minus 7z squared. Then we have 2z minus negative 5z, so this becomes a positive. So this will be 2z plus 5z. So this is 7z here. And then lastly, we have negative 1 minus 2. So this will give us a minus 3. So that's all we do when we're dealing with vertical form. Now in this next example, we're adding 3 polynomials. So it's going to be a little bit more complicated, but it's not going to change our method. We still have these columns, which represent the like terms. So all of the terms in this column is m cubed, so we're just going to add these guys together. We have minus 6 plus 8 minus 3. So this will give us a minus m cubed for this guy here. Then we have 2 plus 4 plus 2 for our m squared terms. So this will give us an 8m squared. And lastly, we're going to add all of our just m terms. So we have plus 5 minus 6 minus 7. So this is going to give us a minus 8m for this term here. Okay. So sometimes adding it in vertical form is a little bit easier. So we can easily see all of our like terms. They're laid out in the columns like this. All right, so in this next section, we're working with polynomial functions, and we're going to start off with the first several examples with adding and subtracting these polynomial functions. So we have these 3 functions, f of x, g of x, and h of x, and we want to find each of the following. So starting with 31 here, we want to find f plus g of x. And if you're unfamiliar with this notation, make sure you check out the textbook, but this is the same thing as f of x plus g of x. So all we're doing for this example is just adding these 2 polynomial functions. So this is going to be f of x, so x squared minus 9 plus our g of x, and g of x is 2x. So rewriting this so that our polynomial function is in descending orders of our variable x, this will be x squared plus 2x minus 9. So this would be our final answer here. Now for this next example here, what we're doing is we're going to subtract these 2 polynomial functions, but there's a bit of a twist. We're going to subtract them when they're evaluated at the x value negative 3. So this is the same as f of negative 3 minus h of negative 3. So what we'll do is we'll plug negative 3 into our x variables into these functions and then subtract those values. So f of negative 3, we're going to evaluate that by just plugging negative 3 into this x here. So this will give me negative 3 squared minus 9. So that's f of negative 3, and then we want to subtract out h of negative 3. So since we're subtracting, I'm just going to put parentheses here. So h of negative 3 we're going to get by plugging negative 3 into this x. So it'll be negative 3 minus 3. So we're subtracting that out. So this will give us negative 3 squared is 9, subtracting 9, and then we're subtracting out negative 3 minus 3, so this will be a negative 6. 9 minus 9 gives us 0, and then we have minus a negative 6, so that'll make this positive, so this whole thing turns into positive 6. Now, something to note here is that we could have done this another way. We could have first subtracted these 2 polynomial functions and then evaluated the result at negative 3. So we could perform the subtraction. Doing so, we're going to get x squared minus x minus 6. Then taken this and evaluated that result at x is equal to negative 3. So plugging negative 3 into the resulting polynomial function. So doing so, we're going to get 9 plus 3 minus 6, and this gives us a positive 6. Okay, so there are a couple different ways we can approach this type of problem. Whichever one is easier for you, I recommend doing. All right, so let's look at another example here, question 38. Now what we're doing is we're going to add these 2 polynomial functions and evaluate the result at negative 2. Or what we can do is just plug in x is equal to negative 2 into each function and then add them together. So we're going to do the latter. F of negative 2 is going to be this guy evaluated at x is equal to negative 2, so we're going to get negative 2 squared minus 9. This will give us negative 2 squared minus 9, and then we're adding to this the value of our polynomial function h of x evaluated at x is equal to negative 2. This is h of x, so we're just going to plug negative 2 into this here. So negative 2 in for x, and then plus 3. Now simplifying this, we're going to get 4 minus 9 minus 2 plus 3, and so in the end, we're going to get negative 10 for this one. So this is equal to negative 10. Now for this next question here, we want to add these two polynomial functions together and evaluate the result at x is equal to 1/3. And so for this one, that's exactly what I'm going to do, and we'll see why in a moment. So first, let's find the sum of these two polynomial functions. So this will be g of x, which is 2x plus h of x, which is x minus 3. So this will be 2x plus x plus 3, which gives us 3x plus 3. Now, the sum of these guys evaluated at x is equal to 1/3 is going to be 3 times 1/3, so just plugging in 1/3 into our x value, plus 3. So this will give us 1 plus 3, which gives us, actually I think, oh yes, our function h of x is actually minus 3. So this should all be minus here. Sorry about that. So in the end here, this will give us a negative 2. All right, so for this particular example, it was easier to first take the product of these, take the sum of these two polynomial functions and then evaluate it at this x value. Sometimes that might not be the case, so it just depends on which way you want to approach it. If we had just plugged in 1/3 into each of these functions and added them together like we did in the last example, we still would have ended up with this answer, but it might have taken a little bit longer to get there. Now in this next example here, what we want to do is graph this polynomial function, and we're going to do so by recognizing its identity function and then using our transformations to graph it. So our identity function in this case is going to be x squared. What's happening to x squared is it's negative and then we're adding 2 to it. So that's going to tell us how to move our identity function. And that's given by this graph here. This parabola is x squared. So first things first, this minus here out front of our x squared tells us that we're going to reflect our identity function across the x-axis. So doing so, we can literally just take these points and reflect it directly across the x-axis here. So we'll do that in green. We'll have these points here. And so this in green here would be the function minus x squared, right? And then lastly, this plus 2 here tells us that what's happening now to this new function is that we're adding 2 to it. So all of these points, we're just going to move 2 units up on our graph here. So we're going to have a point here, and here, and then a point here and here. So this would be the graph of our function minus x squared plus 2. All right, and we also want to find the domain and range of this guy. So the domain is going to be all of our possible input or x values. And as we can see, we're going to have all of these possible values, as this is going to continue on in both of these directions here. All of our possible input values is just going to be all real numbers. So negative infinity up to infinity here. All of these inputs are possible on this number line. Then our range is going to be all of our possible output. All of our, oh, my pencil is not working. There we go. All of our possible output values. So as we can see, this is going to be all of our possible y values. Now the biggest y value we have is 2. But then the smallest y value we have, we can't exactly pinpoint, as this is going to continue on forever. So that means all of these negative values are possibilities, and it's going to be within our range. So it's going to be from negative infinity all the way up to this biggest y value, which is 2. So that'll be negative infinity up to and including that value, y is equal to 2. All right, so these are going to be the last 4 examples of this video, and we're dealing with a composition of functions. So what we're doing is we're composing one function with another, and usually one of the functions are going to be evaluated at a specific value. So we're given these 3 polynomial functions here, and let's start with this example. We have h of g of 4, and we can rewrite this using this notation here, h of g of 4. And so we're familiar with this notation. What this means is we're going to plug this into our x value into this polynomial function h of x. So in order to do that, the first thing we're going to do though is figure out what this value is. So g of 4 is going to be this polynomial function g of x evaluated at x is equal to 4. So we're going to get 2 times 4 plus 3. So this will give us 8 plus 3, which is 11. So if g of 4 is equal to 11, then we're just evaluating our h of x at 11. So what I mean is we have h of g of 4, which is going to be the same as h of 11, which is going to be h of x evaluated at x is equal to 11. So we'll plug in 11 there, and we get 6. All right, let's look at this next example here. Again, dealing with the composition of functions, and we can rewrite it using this notation here. So we're evaluating our function f at this value g of 0. So the first thing we'll do is evaluate g at x is equal to 0. Doing so, we just plug 0 into this polynomial function, and we're going to get 3. So then f of g of 0 is going to be the same thing as f of 3. So we just have to plug in 3 into our x value in this polynomial function. So this will give us 3 squared plus 4, which is 9 plus 4, which is 13. So f of g of 0 is going to be 13. All right, so for this next example, we're evaluating f of h of negative 2. So again, we're just going to use this notation here. We're going to evaluate h at negative 2 and then plug that value into our function f. So the first thing, we're going to evaluate h of negative 2. Just plug in negative 2 into this x here. So this will be negative 2 minus 5, which gives us negative 7. So f of h of negative 2 is the same thing as f of negative 7. So we'll evaluate this by plugging negative 7 into this function. So we're going to get negative 7 squared plus 4. This gives us 49 plus 4, which is 53. So f of h of negative 2 is going to give us 53. And lastly, we're going to evaluate h of f of x. So in this case, we're just going to compose this function with another, and this other function is not going to be evaluated at a specific value. So we have h of f of x. So we're just going to plug this directly into our polynomial function h. We're going to plug f of x, so x squared plus 4, directly into this x value for h here. So f of x is x squared plus 4. So we're going to plug this directly into our polynomial function h. This gives us x squared plus 4 minus 5. Again, just plugging in x squared plus 4 into this x here. And then we still have this minus 5 on the side. So simplifying this, we're going to get x squared minus 1. So the value of our polynomial function h evaluated at the polynomial function f of x is equal to x squared minus 1. Alright, so that'll be it for this video.